history of food is the history of humanity.
A lot of our social life is organized around food.
And it's a story that has continued as man has ventured into space.
The iron content of the astronauts' diet should be lower than the diet on Earth.
In space, I just hated sweet. I remember they gave me a coffee with sugar. I couldn't drink.
One of the Apollo astronauts is very proud that he was the only human who has ever eaten spaghetti on the moon's surface.
As we plan longer missions and future voyages of exploration, research into food and nutrition is at the forefront of the effort to travel to and build bases on other planets in our solar system.
The target for a Mars mission is to be able to recycle roughly 40% of the food.
Most of us in Europe are lucky enough to take food for granted. Yet, if you really think about it, we still spend a great deal of our lives getting, preparing and of course eating the stuff. In fact, for most of human history, the majority of people spent all of their lives just producing the food they needed to survive. And in many parts of the world, this is still the way millions of people live. It was only in the 19th and 20th centuries that many of us left fields and migrated to towns and cities to work in the factories and the offices of the modern world. The reason that food is such an integral part of our lives is because it provides us the fuel that we convert into energy. This tractor needs fuel to work, but instead of running on diesel, our bodies unlock the energy we need from the food that we eat. This makes food and eating a huge part of our lives. But food is much more than just fuel. From the moment you were conceived and began to develop in your mother's womb, your body has been getting most of the raw material it needs to build and repair itself from nutrients in food.
And it's exactly the same in space. To spend more than a few hours in space, we have to take supplies of food and water with us.
I'm a life scientist working for the European Space Agency ESA. At ESA, there are thousands of scientists and engineers involved in research into how we can live in space. We have a big challenge ahead of us. As we plan missions to other planets, we have to find ways of building space farms and actually producing food and water in space.
Many of these projects are being tested on the International Space Station, the ISS. The ISS has been built 400 kilometers above our heads in an international effort of research and space exploration. Traveling at 28,000 kilometers per hour, it orbits the Earth 16 times every day.
But to really understand food and nutrition in space, let's find out exactly why we need food and how we convert it into the fuel and other essentials for life. Any physical or mental activity, let alone competing on this course, our bodies need energy. Every time we speak, blink and even dream, we use energy.
The cells in our bodies use the energy stored in food for everything from building proteins, copying genetic information and of course moving our muscles. Believe it or not, our brains use more energy than any other single organ in your body. Just thinking uses 20% of the energy we need.
3, 2, 1, fire!
How is energy stored in food in the first place? food is mostly made up from three groups of chemical compounds: carbohydrates, fats and proteins.
Back on the road, nice and low.
Carbohydrates and fats are mostly used for energy, whilst proteins are the building blocks for every cell in our bodies.
But what foods do we need to eat to get these essential ingredients? Foods like bread and pasta are full of carbohydrates. We get fats from milk, cheese and vegetable products such as oil. And we get proteins again from animal products or some vegetables such as soy. Food also gives us the important minerals and vitamins that our bodies need to rebuild themselves and control vital chemical reactions.
Like the crude oil that is pumped out of the ground and then converted into the petrol and diesel for our cars, our bodies have to process food to get to the stored energy that is chemically locked up in food. The first part of this process is digestion. Go!
As soon as food has entered the mouth and the fats, proteins and carbohydrates have begun their journey through the body, the process of digestion begins. Digestion is a process that requires food and gives off heat and energy. It does this by breaking down the complex molecules of food into simpler, more readily absorbed molecules. Digestion happens as the food travels along the alimentary canal or our gut. The gut is a muscular tube that uses peristaltic action to squeeze the food from our mouth to our anus via our stomach and intestines. During this passage, nutrients are extracted from food in several processes. This starts in the mouth, where food is broken into small pieces by the mechanical act of chewing. Our salivary glands also get to work and produce an enzyme called amylase, which breaks the chemical bonds in carbohydrates, releasing sugars.
The partially digested food is then transported through the esophagus into the stomach. The churning action of the stomach further breaks down the food and mixes it with gastric juice.
The stomach is a muscular sac. When empty, it's the size of a sausage, but it stretches to the size of a large melon when full. Food remains in the stomach for between 30 minutes and 4 hours. In the stomach, zymogen cells secrete pepsinogen, which is converted into protein-splitting enzyme pepsin. The gastric juice in the stomach is mostly hydrochloric acid and is about 1 million times more acidic than tap water. It provides the optimum pH for pepsin and also denatures proteins into polypeptides and softens connective tissue in meat.
The next stage of digestion happens in the small intestine, where further enzymes break down the polypeptide chains into amino acids, carbohydrates into glucose, and fats into fatty acids and glycerol. These are the end products of digestion.
These simple molecules, together with the vitamins, minerals and water, are then absorbed into the bloodstream in the small intestine and transported to where they are needed in the body. The most important energy molecule that the digestive system extracts from food and transfers to the bloodstream is glucose, commonly known as blood sugar. If you have low blood sugar levels, you will have a lack of energy. Excess glucose is stored as glycogen in the muscles and the liver and converted back into glucose when required.
Glucose is supplied to our body cells by the bloodstream. But our cells cannot get the energy directly from glucose, so they convert it into a form that they can use, the molecule ATP.
Glucose molecules are broken down by a process known as cellular respiration. This process consists of 3 of life's most important biochemical reactions: glycolysis, the Krebs cycle, and the electron transport chain. Collectively, the system converts each glucose molecule into approximately 30 molecules of ATP. It's an extraordinary fact that the billions of cells in our bodies produce half of our own body weight of ATP every day and then burn it for energy. After the digestive system has extracted all these vital ingredients from the food we eat, what's left passes to the large intestine, where water is extracted and waste material is produced, which eventually passes out of our bodies. So that's how our bodies digest food. But exactly how much and what kind of food should we be eating to stay healthy?
We've seen how our body gets the energy and the building materials that our bodies need from the food that we eat. But exactly how much food do we need?
To understand this, we have to carefully calculate how much energy is contained in food. One way of measuring this is with a bomb calorimeter. The energy in food is counted in kilocalories. Common usage has shortened kilocalories to calorie. 1 calorie corresponds to the amount of food that when burned will raise the temperature of 1 gram of water by 1 degree Celsius. The average grown man needs approximately 2,500 kilocalories a day and women about 2,000. A lot of the calories we consume are needed just to keep us alive, before we do any work. This is called our basal metabolic rate, and we use between 800 and 1400 calories to keep our brain, heart and all our other organs ticking over. A balanced diet that supplies the correct amount of calories and nutrients is fundamental for a healthy body and a healthy life. Our nutritional needs depend directly on the amount of work our bodies do. A sports person needs many more calories than someone who spends all day in an office or classroom getting very little exercise.
If you consume more food than your body actually uses for energy, it is stored as fat. Our bodies have evolved to store excess energy supplies in fat, in case we need it for the future when there is a food shortage. The trouble is that for most of us in the developed world, we usually have plenty of food and don't need to rely on stored fat.
In the last 2 decades, sedentary lifestyles and unhealthy diets has led to the problem of many overweight adults and children worldwide. Being overweight is a major contributor to serious diseases such as high blood pressure, cardiovascular disease and type 2 diabetes.
If we eat more than our bodies need, our diet is said to be unbalanced.
In space, an astronaut's food intake has to be the ultimate balanced diet. They have to give top performances every day in the most hostile environment in which human beings can survive. So their food has to be both nutritionally balanced and tasty, but weigh as little as possible. A wrong estimate of their nutritional needs may be harmful to their health. It can lead to tiredness, muscular atrophy and cardiovascular problems. So the astronaut's diet is carefully monitored whilst in space by flight surgeons like Dr. Filippo Ongaro.
The nutritional intake is monitored in the sense that we know what has been brought on board for that astronaut. So we're able to know in terms of nutrients and in terms of calories what the astronaut is going to eat. And that choice has been made on the basis of the needs that the astronaut has that has been calculated on Earth, including, of course, the physical exercise. On the space station, the astronaut is exercising a couple of hours per day, so there's a lot of calories that are burned just by physical exercise.
Extensive research has shown that astronauts actually use slightly fewer calories when in space. But it's not just calorie intake that needs to be monitored in space. ESA nutritionists have discovered some important differences between a balanced diet on Earth and a balanced diet for an astronaut in space.
The iron intake in space should be lower than on Earth, because in space the astronaut has a lowered plasma volume and a lowered erythrocyte volume. So at the beginning of spaceflight there's a breakdown of the hemoglobin, which contains the iron. So more iron is available. So that's one of the exceptions. The iron content of the astronaut's diet should be lower than the diet on Earth.
Vitamin D is also very important for healthy bones. Our bodies usually make vitamin D when our skin is exposed to sunlight. Spacecraft are shielded to protect the astronauts from harmful radiation and excess sunlight.
Astronauts in space in the ISS don't have that much sunlight, so they can't synthesize vitamin D. So what we right now add is about 800 international units of vitamin D with the space food.
But it's not just about what we eat. When we eat can also drastically improve our performance. This is where astronauts can learn from the field of sports science.
Well, there are many parallels in what the physician is doing together with the astronaut. Is very similar to what a coach or a medical doctor does together with the athlete. So it's really improving, optimizing his level of health from a mental and a physical perspective.
Here at Helium Thames, some of the world's top rowers train to achieve their optimum physical and mental performance. Olympic rower Tony Garbutt knows all about getting the optimum performance out of his body.
How important is a balanced diet for an athlete like you to keep fit during training?
Well, I find it really important to make sure you eat correctly. The big thing we talk about, I guess, is carbohydrates, because without the glycogen stores, which is what's stored in the muscle, that is absolutely key. And if you get that wrong, you're going to be in trouble. What I advise people really is to try and look at what they call complex carbohydrates, which is bran, porridge oats, wholemeal bread. Gives you the energy for a little bit longer, so you don't have the dips in energy, thus the dips in performance. When we go into more slightly weight-based training, I always try and think about having more protein as well. So I combine the two together, and they've done some recent study to show that actually taking on protein and carbohydrate after hard strenuous exercise within a 20-minute window helps recuperate the body. But it's effectively quite a natural, balanced diet, really. It's quite simple stuff, but just making sure that you're having it evenly spaced out throughout the day in regular intervals.
So we've heard how food can be used to optimize an individual's physical performance. But there's a lot more to food than simply its effect on the body.
As important as food is, as the fuel and the raw material bodies need, it's not the only reason we eat. Another very important role food plays in our lives is a psychological one.
Eating and sharing food with other people is probably the oldest communal act that we know of. It's no exaggeration to say that the societies we live in today had their beginnings in the act of obtaining and sharing food in groups. You can see this in all social animals. Long before we started farming, we worked together hunting and gathering our food. The eating and sharing of food forms the basis of societies throughout the animal kingdom. Nowadays, this has of course changed, and we get most of our food from the supermarket, and we eat alone a lot more than our ancestors. But eating together is still a fundamental part of our daily lives. And the importance of it is recognized by astronaut psychologist Professor Dietrich Manzai.
If we want to socialize with friends, with other family members, even with people we do not know very well, we make appointments for a common dinner or a common lunch. We have work lunches. So a lot of our social life is organized around food. The ISS is big enough that maybe astronauts do not meet too much during the day. So what we have decided for the ISS program is that we want the crew at least once a day to have a common meal.
We make sure that the dinner at night is made all together. So you have the time of the dinner and the time after. You can talk together, have a social event, discuss, have joke. And this is important for the cohesion of the crew.
We want at least to give them possibilities to communicate informally together, and this is highly valued, I think, from my point as a psychologist.
The table is very small for 6, but you have to find a way to be all together and to prepare your food. Then you have the special food for Christmas or for a birthday. We bring some food for a nice chef in Europe, and this is really appreciated by our own astronauts, but also by the whole community of astronauts.
Food is also a kind of national thing. So to get food from your home country, which probably most fit to your personal preferences, I think is very important from time to time.
We've seen how crews on the ISS get to change from a range of food particular to their own personal taste and culture. This demonstrates a huge diversity of foods that different cultures have as part of their staple diet. However, as diverse as the food we've grown up with is, and is now available for cruise in space, it wasn't always so.
The food that the first astronauts experienced is a testament to the pioneering spirit. They had to endure cubes of cold, dehydrated food that relied on their own saliva to rehydrate, and tasteless paste squeezed out of toothpaste-like tubes.
The food was unappetizing, and not surprisingly, they really disliked squeezing it out of tubes directly into their mouth.
By the time of the Apollo moon missions in the late 1960s, the quality and variety of food had improved enormously. The Apollo spacecraft had hot water, which made rehydrating foods easier and improved the taste. And for the first time, astronauts were able to enjoy their food in space.
One of the Apollo astronauts is very proud that he was the only human who has ever eaten spaghetti on the moon surface.
In the 50 years since we first put humans in space, space food went from unappetizing concoctions to 3-star dishes made by some of the world's most renowned chefs.
ESA has cooperated with European chefs to provide high-quality space food. They also created special meals for astronauts to celebrate New Year, birthdays and the arrival of a new crew. Over 200 recipes are now available. During training, astronauts are invited to choose which meals they would like to eat on their next mission. Dishes range from chicken teriyaki to fruit salad, beef stroganoff and butterscotch pudding.
A few months before the mission, they make you choose between something like 500 different meals, and you test the food, not in one day because it will be very hard, so you do that in different days, and you can say, I prefer this food, and you can say, I don't like this food. But the nutrition are looking at your food in terms of a balance of vitamins and quality for your body. So even if you don't like a type of food, you might have it in your package. I remember for my flight, for instance, I was surprised because for breakfast I had fish. We have croissant and cafe, but you don't have fish, so you have to get used to it.
But it's not just the odd, nasty surprise in their food package that astronauts have to look out for. It seems that spending time in space affects the astronauts' sense of taste.
What astronauts anecdotally tell us is that they lose taste and smell sensations in space, and that's probably one of the reasons why the space food is so high in sodium content, because more salty food tastes better than other food.
For me, I like salted food, but in space I wanted even more salted food, you know. And on the ground I don't like too much sweet, but in space I just hated sweet. I remember they gave me a coffee with sugar. I couldn't drink coffee with sugar because it was too much sugar. So your taste has a tendency to change a little bit in space compared to the ground.
Having created this fantastic range of foods for astronauts, the next consideration is how to get it into space. Even a great chef's food has to be preserved before it's taken into space.
Food scientist Mike Lewis is responsible for developing techniques that will preserve astronauts' food. But he is just the latest practitioner of techniques that have been used for millennia.
Mankind has been preserving food in lots of ways, going back 4,000 years. Salting, sugar preserving, food preservation is very, very old and very traditional. Well, the main purpose of preserving foods is to inactivate the microorganisms or microbes that are naturally present.
All preservation methods involve preventing the growth of bacteria, fungi and other microorganisms, as well as retarding the oxidation of fats, which cause rancidity. In today's high-tech food industry, a variety of techniques are used to preserve food, many of which we may not even be aware of. foods that we buy may have been chilled, disinfected or irradiated in order to slow down microbial action. Most of the food consumed by astronauts in space has been preserved in some way. The two most common methods of preserving space food are sterilization, where food is heated to 121 degrees centigrade in a sealed can, and dehydration, where water is removed, hindering the development of microbes and reducing the volume of the food. But whichever technique is used to preserve food for use in space, the original properties of the food are inevitably altered. And George Grimble is researching the consequences of this.
Does food preservation degrade the quality of food and degrade its nutritional value? And the answer has to be that it depends on the process that's being used to preserve the food.
A lot of research has gone on to try and minimise nutritional changes during food processing. For example, peas, if you buy them and they've been on the market stall for 2 days, would have lost a considerable amount of their vitamin C. And one of the advantages, for example, of quick freezing is to minimise those sorts of changes.
What you'll often find is that particularly sensitive components in food, for example vitamin A or vitamin E, can be degraded by atmospheric oxygen. And what this means is that you have to take into account during the processing the amount of vitamin that's degraded and then add an amount back into the food to make sure it reaches the right level.
Astronauts don't have to rely only on preserved food. The ISS gets resupplied every few months, so astronauts occasionally enjoy fresh food when a resupply craft has just arrived.
The biggest differences between space food and food on Earth are the packaging methods. Space food must be carefully contained so it doesn't float around in the free-fall environment.
The food has to be kept in a kind of sauce. If it is too dry, like if you took a rice too dry, the rice will fly over.
Loose food particles on board the ISS could cause serious problems, not only for the machinery of the spaceship itself, but for the astronauts' health.
This is dangerous because you can eat your eyes, but moreover you can breathe it, and you can put that in your lung, and this is very bad.
For this reason, things as common as salt and pepper have to be provided in a liquid form.
But liquids can float away as well, so drinks like coffee, fruit juice and tea are packaged as powders and sealed in squeezable containers. Astronauts just add water to the drinks to rehydrate them and drink them with straws. The ISS has a kitchen that is equipped with food storage compartments, food warmers, a food preparation area, a table with restraints so the astronauts don't float away whilst eating, and metal trays that stop the food packages from floating away.
But this all depends on food that is regularly resupplied from Earth. In the next section, I'm going to find out how ESA plans to feed astronauts on missions lasting as long as 3 years. Here, on the International Space Station, the next meal is only a supply ship away. But how do we feed a crew of 6 astronauts on a 3-year mission to Mars?
ESA and the other international space agencies are planning manned missions to the Moon and Mars in the future. For that length of time, a crew of 6 would need many tons of food and drinking water, let alone all the other vital supplies that they would require. Scientists are researching how to extend the shelf life of food for up to 5 years, whilst maintaining a variety of great-tasting foods. However, the most powerful rocket in the world today can only carry a payload of a few tons into space, and a trip to Mars would need many tons of food and supplies.
The only practical way to supply long-term missions is to launch the equivalent of a farm into space and grow at least some food, whilst recycling water and waste to supply the crew for long periods of time. When we start to build bases on the Moon and Mars, we also have to grow food and recycle waste. to enable us to stay on these distant planets for years at a time. ESA has a number of research projects for growing and recycling food into space.
ESA scientist Christel Payet works on one of these, the Melissa project.
The Melissa project addresses actually the supply of air, water and food for the crew in a closed regenerative system, in the sense that we take actually the waste which are produced by the crew, being fecal material, urine, that we degrade, and from that we regenerate the water, the air, and we produce as well food.
Today, the target for a Mars mission is to be able to recycle roughly 40% of the food. Why 40% of the food? Because if you recycle or produce 40% of the food of the crew, directly you produce 100% of oxygen and 100% of the water that the crew will need.
The question of which foodstuffs to actually grow in the precious reclaimed resources is not simply a scientific one.
There is another criteria which is very important, is the quality of the food you will need to produce. You can fill the requirement in terms of nutrition with wheat only, but you have to consider the acceptance. And if we feed the crew with only wheat, of course we will have probably some difficulties.
You just want to eat a fresh tomato or fresh cucumber or a fresh fruit.
Melissa has already successfully trialed a closed water recycling system, but this technology is not just applicable in space.
You know that today everybody is challenged by the environmental issue and the global warming issues specifically, the water quality, the air quality, the contaminants and everything. And we know already, because we have some success, that the Melissa technology is applicable to Earth, which are already used in the terrestrial application. And I think it's important that people realize this.
Since the beginnings of the exploration of space, there have been many technological spin-offs, from advanced composite materials to GPS that we all use in our phones and sat-navs every day. And in a world of increasing population and decreasing resources, systems such as Melissa, developed for space travel, could be the most invaluable spin-off yet.
We've seen in this program that food is literally the fuel of life, on Earth and in space. Ensuring adequate supplies of food always has and always will be the most important activity that all living things, from plankton to planetary explorers, do.
As we've seen, the logistics of long-term spaceflight require huge technological innovations to supply crews with the food they need, both for their physiological and psychological well-being as they travel to distant planets. The Earth is a self-sustaining ecosystem. A manned spacecraft that will be away from its home planet for years will also have to be a self-sustaining ecosystem. Or to put it another way, a miniature planet Earth.
In many ways, the technological challenges for ensuring future food supplies on Earth are the same as in space.